My name is Kristen Manuzzi, and I'm a product manager with National Instruments. Today, we'll be talking about best practices for building automated test systems, specifically for advanced aerospace and defense electronic systems. I want to start by saying that best practices depend on your perspective. If we were talking about consumer electronics, we'd be talking about leveraging FPGA technologies to squeeze out every millisecond of test time. However, many of you might be aware that the B-52 bomber has been in service by the U.S. Air Force since 1955 and is expected to be in service well into the 2040s. When thinking about best practices for the ground support equipment or subsystem test stations supporting platforms like the B-52, the concerns are going to be far, far different. This session is focused around the best practices for architecting stable, long lifecycle, high-mix test platforms. One of the biggest challenges is the mental shift from reactive system development to proactive system development. What I mean is that I've seen many teams win a bid or a contract and then start specifying equipment, building test code, and plugging away at building the test station to meet their deadline and budget. There's definitely nothing wrong with this approach, but it's the mature test organizations that are able to take a step back, evaluate their existing software infrastructure and libraries, and build a scalable, supportable test station that are successful in the long run. Both teams may be able to deliver a tester on time and on budget for the application or program, but one is going to be far more equipped to handle the long-term maintenance and total cost of ownership expenses than the other. Here's that same scenario in terms of a tester lifecycle and total cost of ownership. Probably not as big of an issue for those companies testing semiconductor or mobile devices because the tester lifecycle may only be 12 to 18 months. But for aerospace and defense applications, those costs can add up over decades of support. This session will give you some of NI's best practices for developing, deploying, and maintaining test stations to reduce your total cost of ownership for your test systems. NI is in a unique position in the test and measurement industry. We've been supplying PXI systems for automated test for nearly 20 years and have built up a tremendous library of knowledge of test systems across customers, industries, and continents. We use this collective knowledge we've gained to engage in what we call business and technology assessments to help test engineering and maintenance organizations hone their test engineering strategies and optimize their operations to whatever key performance indicators are most important for their business. One such example of that engagement is at Harris, where we collaborated to decrease their total cost of tests by 74%. With a growing business unit that was quickly outscaling the factory, it was also important to avoid any facilities, IT, and other overhead with acquiring additional factory space. Here are the 3 best practices for architecting an automated test system that we'll dive into. Software knowledge and IP is the single most strategic asset to your test engineering team. Great organizations grasp and utilize software architectures, code reuse, and modularity to turn their test engineering organization from a required cost to a strategic asset with the company. We'll spend the next few minutes talking through software best practices before we move on to instrumentation and infrastructure pieces of a test system. The best way to develop an automated test system is to follow a modular software architecture to increase reuse and reduce validation cost as components change. Code modularity isn't a novel concept, but we're talking not just about modular, but about a layered approach. This is an example of the products that NI offers that fit into each of these architectural layers. NI has over 40 years of experience and billions invested in various products and technologies throughout the software layers of a test system. We started out as a GPIB company in the 1970s, created LabVIEW and Lab Windows CVI in the 1980s, and then introduced TestStand that has become the multiple industry standard for test management software. We often get the question, what should be in the test management software layer versus the TPS or the test code layer? Obviously, this can depend on the layering implementation, but here's a good rule of thumb. Keep anything that's DUT specific in the test code. Keep anything that spans DUTs, DUT families, or tester families in the test management software. One piece that often generates good discussion is around limit testing. Should that be in test management or in the TPS itself? Obviously, it's DUT specific, but the framework for testing limits fits best at the test management level, such that you can modify limits without having to revalidate test code. TestStand is an industry-leading test executive that provides an out-of-the-box framework for this separation of test responsibilities. TestStand is a graphical environment for developing, executing, and deploying test sequences. It can call just about any piece of test code, allowing for the unification of current and legacy test code easily into one test sequence. It can also test in parallel and generate results or log to a database in a variety of formats. TestStand has been the leading commercial off-the-shelf tool for test management software since its release almost 20 years ago. It has a wide reach of industries and customers served, as well as a rich ecosystem of community and partner resources. As an example of the benefits that commercial off-the-shelf tools can bring to your software architecture, let's take a look at just how much time can be saved when starting with TestStand as your top-level test executive versus architecting from scratch. Building and maintaining in-house test executive software can be exhausting. The user interface, sequence development environment, database integration, and interface with various test development languages are just a few of the components you must maintain with this in-house approach. The graph above shows the average man days required to develop these basic features of a test executive according to the results of polling that we did with actual NI customers. Now, obviously, not all of the above features are going to be critical for every customer. If a company only operates domestically, then localization may not be necessary. If they only have a few long tests, then parallel testing is likely not a requirement. Many of these, however, are essential features that a company would need in order to move forward with their projects. When we start looking at other layers of the software stack, the area that TPS developers spend most of their time is in the ADEs, or application development environments. Aside from just LabVIEW, TestStand has native support for ADEs that call C, C++, and .NET, and also has custom plugins for things like Atlas, Tcl, Java, V, and Python. This is critical when you have TPS developers that are highly skilled in a given language and you want to capitalize on that development efficiency. And more importantly, be able to support legacy code written by someone who left the company or left the team. Typically, your TPS isn't just this nice piece of code written in LabVIEW that is completely self-enclosed. It's usually talking to a piece of test equipment that is communicating with, stimulating, or measuring the device under test. This couples both the ADE and the instrumentation, sometimes down to the specific driver version or model number. Going back to some of our opening comments, this works fine when you're testing a consumer device that only has a life cycle of 12 to 18 months. But when you're supporting a tester for years or decades, you need to plan for replacements. We'll talk more in the hardware section, but let's briefly touch on hardware abstraction and measurement abstraction approaches. Let's talk about where the rubber hits the road and where theory meets practicality. In reality, if you just won a program contract, there's going to be no line item for software architecture development. This is typically funded by IRAD, or internal R&D cost. The good news is that you can take a multi-phased approach to implementing abstraction. If you're using NI equipment, we already implement hardware abstraction into our family drivers, such that you can swap out products without rewriting TPSs. For those of you adopting IV driver classifications, you have much of the same capability. Even doing as little as reusing DUT control code or APIs across different DUT types is a step in the right direction for abstraction implementation. And the rest you can implement depending on your business needs and resources. Here's a quick look at where hardware and measurement abstraction layers fit into the architecture that we showed previously. Let's look at a quick example of how NI has implemented driver abstraction in our multimeter family. We offer the same NI DMM driver API from 1.0, released in 1998, through the most recent version, making it easy to upgrade to newer or better DMM options. This is especially important for LabVIEW users because many other vendors have different LabVIEW drivers for each DMM family, which can require large amounts of software investment to upgrade. A great example of software standardization and architectural best practices can be seen at L3. L3's automated test engineering team used TestStand and LabVIEW and was able to see a 9 times reduction in test development time and over 60% code reuse. Next, let's switch gears and talk about the hardware pieces of the test system. Working in aerospace and defense, you're probably already familiar with terms like modularity and COTS, or commercial off-the-shelf. In fact, you may have already standardized on an open platform and reaped the benefits of that standardization over the years. Obviously, one of the biggest concerns in building test stations for the DoD and aerospace and defense customers is longevity. PXI has been around for nearly 20 years, and instrumentation vendors are only increasing the level of investment in this platform. With over 2,000 modules available from over 60 vendors, this is a standard that is built to last. If you're not at least considering PXI as the core of your automated test stations, you're definitely behind the curve and putting your test strategy at risk. Now, my intent is not for this to become a product pitch, but I know that not everyone might be as well versed in the NI catalog of instrumentation. So I wanted to take just a moment and speak to some of the innovation in our platform. In 2016, we announced our second generation vector signal transceiver. We've improved upon the vector signal transceiver in every way, offering a 5 times larger FPGA for user customization with LabVIEW, and a 5 times increase in instantaneous bandwidth up to 1 GHz. It's important to note that a critical part of the VST's success and continued success is the software-centric nature of the instrument. Another source of unplanned cost and support is around cabling. It's likely that you may have adopted a station like this from someone who has left your group, and I bet their documentation was not too great. Well-planned mass interconnect solutions, instrumentation test adapters or ITAs, and fixture planning can save a lot of money in the total cost of a test station. At NI, we've heard customers express some of the following sentiments. Man, I wish we could have just spent the money and gotten a clean mass interconnect system. I really didn't think we'd have this many product variants running on the station. Or, there goes a lot of custom cables in this bill of materials. I sure hope one of those doesn't go end of life before we start ramping production. Now, that being said, it's always difficult to make the call of upfront investment versus long-term costs. So let's talk about that a bit more. I'm not going to go into a what-is presentation on mass interconnects, but I do think it's worth showing how the pieces come together with a PXI system to interface to your DUT. From our experience at NI, a typical mass interconnect solution from MacPanel or VPC is going to be around $15,000 US. This can obviously vary greatly depending on quantity and classes of instrumentation, but for a high-mix PCB test station with a dozen or so PXI modules, that's a good estimate. Some recommended considerations for deciding on whether or not to adopt this type of solution. Number 1, what's the volume of units going through the tester? Lots of connections and lots of throughput is a sign that mass interconnect is probably a good choice. Number 2, what's the mix of products going through the tester? It's often preferable to design a new fixture for different DUT types that can mirror the life cycle of the product as opposed to fixed docking and cable management. And number 3, are you planning to replicate the system? From a documentation, build, serviceability, and thermal validation standpoint, a mass interconnect will save you time and energy. Another approach to consider is making intelligent fixtures part of your test strategy. If there are very unique unit under test communication protocols that you don't want to burden your high-mix test station with, consider adding that to the DUT fixture for that specific product. Also, consider designing multi-unit under test fixtures that provide feedback to the test station if sockets aren't being used so that the test station can adapt to volume. Now, a serious consideration, how many unique power supply models are in your test stations? To give you a reference point, We had a senior test manager present at our annual test leadership forum that coincides with NI Week on their standardization efforts, and he mentioned that they have over 100 models of power supplies. With a concerted effort, they consolidated that down to just a few. You'd be surprised how much of an impact something like this has on your total cost of test. It's far more than the incremental few $100s in a capital expenditure that you might pay for the standard power supply. It's the calibration cost, the documentation cost, technician and support costs, software maintenance cost, and lifecycle management costs. This year at NI Week 2017, we're excited to announce a new core configuration offering from NI. These out-of-the-box ATE systems provide the ultimate balance in standardized core components to simplify design and documentation, along with the layout flexibility for PXI, compact DAC, and other instrumentation. ATE core configurations can help you accelerate system design, reduce integration burden and risk, and reduce time to deployment for an automated test system. These systems have scalable mechanical and power profiles to cover applications ranging from basic validation bench design to high-power, high-reliability, globally deployed test stations. You can customize the instrumentation in a system using the PXI Advisor. There are configuration rules within the application to ensure the configured system maintains mechanical keepouts of equipment as well as basic airflow considerations to help improve overall layout before purchase. NI offers worldwide shipping, stocking, and serviceability for these systems. Finally, our third best practice, expect the unexpected. Know your system well enough to know where you're going to have lifecycle issues and when. There are both proactive strategies and reactive strategies to managing the lifecycle of your test station, and both are important. On the proactive side, selecting modular architectures has its benefits, such that even if you can't get a pin-compatible replacement, you can at least localize your changes to a single slot to minimize documentation changes, minimize power budget changes, minimize system thermal revalidation, etc. It's also extremely beneficial to have a strong partnership with your vendors to share technology roadmap information. This will keep you up to date on what's going end of life soon and what the latest products are to hopefully have the longest life cycles. Planning system downtime for upgrades is also very important. Best-in-class companies will typically have technology insertion cycles at specific time intervals, allowing them to make multiple upgrades and validate these changes all at the same time. Once the system is deployed, you pretty much need to be reactive. No matter how much you plan, things will come up. Some options for being reactive are finding different products that can meet the same requirement, emulating old instrumentation, performing a large enough last time buy to provide sparing for the remaining life cycle of the tester, or redesigning parts of the test system. We'll talk through each of those, but I wanted to start with an example of how you can work with NI to do system life cycle analysis. This is an example of a system-level lifecycle analysis that NI is happy to perform for our customers. This can be performed for both new designs that have a concern for long life cycles or as a check-in exercise during a technology insertion to get the latest update on the life cycle of a current test system's components. Contact your NI seller to learn more about system-level lifecycle analysis. The simplest path to planning for obsolescence is to work with your supply chain for the test system to ensure long-term support. This is yet another reason to simplify the number of vendors and the bill of materials for a test station. From an NI perspective, standard service programs are available for all hardware and extend up to 5 years. Long-term support options allow you to extend beyond that up to 20 years, and we can definitely work with you to find the right solution to meet your needs. One example of this type of collaboration is a lifecycle analysis review and support contract that we set up with the folks from CACI for the CBATS program. By collaborating on the needs, roadmap, and technology insertion cycles, we were able to significantly reduce the overall maintenance costs for the program. A more innovative approach to managing obsolescence is showcased in the collaborative efforts between NI and Astronics Test Systems. Between NI's history and expertise in designing and building PXI instruments and Astronix Test Systems history in VXI, system integration, and TPS development, we're working to bring a bunch of legacy VXI technologies into the PXI form factor and simplify a transition from VXI to PXI. These products maintain some of the front-end analog circuitry and driver compatibility of many legacy devices to ease the migration process. Lastly, the most innovative approach to managing obsolescence is to look at using synthetic instruments, or FPGA-based instruments. Many times, legacy instrumentation may have lower specifications, clock rates, or simply different capabilities, such as unique triggering. These devices therefore perform differently than the newer replacement instruments and may cause older TPSs to fail, since test limits were defined around the performance of the old instrumentation. One solution to this is for the new instrument to emulate the older instrumentation. FPGA technology has recently made instrument emulation easier for customers, as they allow hardware-level modification based on software. Thanks to LabVIEW FPGA, non-FPGA experts can perform DSP algorithms on FPGA-enabled instruments to emulate older instrument behaviors. An example of software-defined instrumentation can be seen in Radix's test system for real-time spectrum analysis. For those that are interested, NI actually ships some great resources and off-the-shelf hardware abstraction and measurement abstraction capabilities as part of our actor framework and measurement utility plugin for TestStand. Obviously, every test system is going to be different. Whether you're looking at building a new dedicated tester for a high-volume product, building a new high-mix platform, or trying to maintain a tester from 1975 for the B52 platform, you're going to have your unique needs. This session hopefully gives you some things to remember when you're making localized decisions about your tester, and the value of thinking about leverage, longevity, and lifecycle collaboration along the way. And even if you get stuck, don't worry. We have your back. We have over 500 applications engineers and 170 systems engineers to support you along the way. Wherever you send your test systems, we'll be there to help.